So, welcome to the lab section. So there's going to be 6 labs in the course, and the lab attendance is mandatory. And this is important because we're going to be covering a lot of basic stuff that you guys are going to need in order to write the lab reports after. So there's going to be 6 labs. The first lab is the one that we're doing right now. It's going to cover HFSS and ADS. And then labs 2 to 5 will be different designs using both HFSS and ADS. And then finally, lab 6 will be an HFSS lab exam. There's going to be 4 reports for labs 2 to 5. So this lab will not have a report. For each lab, I will upload the report guidelines for you guys and explain everything that I will be looking forward to see in your reports. The lab reports must be completed using the IEEE 2-column format and typed on LaTeX. If you guys are not familiar with LaTeX, Overleaf has a lot of good tutorials explaining how to use LaTeX, and you can use Overleaf itself for that. And for IEEE templates, you can find them on Overleaf, or I'm sure you guys can find them on the IEEE website itself. The lab reports will be due 1 week after each lab at 11:55 p.m. Except next week, of course, because there's no lab report for this lab. And my office hours will be by appointment on Zoom. I noticed that a few people tried to join in on Zoom now. Unfortunately, I don't have the paid account, so I can't do this meeting on Zoom. But my office hours will be on Zoom, and the details are on the lab section page on CUlearn. All right, so the software that we're going to use a lot this semester is HFSS, and it stands for High Frequency Structure Simulator. It's used to analyze structures from an electromagnetic point of view. So for example, you can analyze antennas or the radar cross-section of aircrafts and transmission lines. And something that you don't need to know in order to use the software is that it uses a numerical technique called finite element method. And it's good to have an idea of how it works. So the idea is HFSS will take up the structure that you want to simulate, and it's going to break it down into smaller structures, and they're called tetrahedra. And then it's going to solve Maxwell's equations for each of these small structures, and it knows how small to break it down based on the meshing criteria and the refinement or convergence criteria that you set. So the solution can be as accurate as you want it. But of course, if you want to get a very accurate solution, that usually means you have to run it for a longer period of time. But the idea is you, the user, will set the convergence criteria, and you always have to check for conversions to make sure that the results make sense. So HFSS will not tell you if the results are correct or not. You have to figure this out for yourself, and we'll go over that today. So the HFSS design process is on this slide, and I want you guys to always, whenever you design something, to go through this process to make sure that you've done everything right. So the first step is to design the model of your structure. So in HFSS, we're dealing with 3D structures. So it could be a combination of boxes or cylinders or surfaces. So the first step is to design the structure on HFSS, and it works like any CAD modeling software. And then the next step is to define the boundary conditions. So HFSS needs a set of boundaries, or the structure that you're simulating has to have bounds, right? It's not infinite in extent. So you have to define where the structure starts and where it ends, and what boundary, what electromagnetic boundary HFSS is going to use. And then the third step is to define excitations or ports. So HFSS needs to know where the energy is coming from and where the energy is going to end up. And these are the ports that you define in the software. And then the fourth step is to define a solution setup and the frequency sweep and the convergence criteria. So you're telling HFSS what frequency you want the solution to be solved at. And what convergence criteria that you find acceptable. And if you want to look at a frequency sweep, you're going to tell the software, I want to see the results from this frequency to that frequency. You're also going to tell it what type of sweep, if you're interested in just viewing maybe just the S parameters, or if you want to view a visual of the fields inside the structure. So this would be defined in the solution setup. And I already mentioned the frequency sweeps. So these sort of come in hand. And then here, this is just clicking a button to validate that your design is correct, that it meets all the criteria for a simulation. And then simulate, again, you just hit a button to simulate. And then for the results, you plot the results from the data that you just solved. And so this process, we'll just keep it in mind. We're going to be designing 3 structures today. And for each structure, I'm going to be talking about these design steps. All right, so for the solution types, the default solution type is called driven modal, and that will be pretty much the one we use for every design in this course. Other solutions are also possible, but they are more involved, and we're not interested in them in this course. For excitations or ports, there are 2 main types, a wave port and a lump port. The main difference between the 2 is that the wave port excitation has to be at the edge of your solution space. So if you're designing a waveguide, your excitation will be at the edge of the waveguide. You cannot excite it in the middle. On the other hand, a lump port gives you the option to define an excitation inside the structure. So it gives you a little more, there's more you can do with lump ports. But again, in this course, we'll be focused more on wave ports because they're more straightforward to define. And for the sweep types, so I have some summaries here for each of the sweep frequency sweeps that you can define, and I will upload the slides on CLearn so you guys can take a look at them later. But the main thing you need to know is a fast sweep, as you would have guessed, is the fastest frequency sweep that you can run, but it's not the most accurate. It's really good if you want to run a lot of frequency points and you wanna see some sharp resonances. So as opposed to other sweeps which can take a long time to run, this one is very fast and can show you resonances in your structure. Another advantage of fast sweep is that it will always process the fields inside the structure, which is good, but again, you have to keep in mind that it's not the most accurate. The second sweep type is called interpolating sweep, and that one is it takes a bit more time than fast sweep, but it is more accurate. But the disadvantage is that it does not give you the field data. So if you want to have a visual of the field inside your structure, an interpolating sweep will not give you that. But it's really good if you want to run a very wide band simulation, which, as opposed to the discrete sweep, which we'll talk about later, it doesn't take that much time. And finally, the discrete sweep. This is the most accurate sweep that you can run, but it does take a lot of memory. And if you want to run it, you only usually run it for a few frequency points. And the big advantage of discrete is that it will save the fields for your solution. But again, this one, it will run the simulation pretty much again every time. So if you have 10 frequency points, you're running the same simulation 10 times. So that takes a lot of RAM and a lot of time. All right, so today we're going to design these 3 structures: a rectangular waveguide, a microstrip line, and a coax cable. And let's get started. So these are the dimensions for the rectangular waveguide. So you guys don't have to remember that. I'm gonna show you on the software. These are the dimensions and properties of the microstrip line, and that's for the coax cable. So again, I have all of these, so you don't have to write them down. All right, so I assume that all of you guys have access to the server. So I'll give you guys some time to log in or VPN in or whatever you need to do. So we'll come back in 2-3 minutes, and then we'll start HFSS. Is this PDF posted somewhere to use as a reference? Yes. Yeah, you already figured it out. Yeah. Adam, can you see my screen? Okay, so you can see that I'm on the server. Perfect. All right, so we'll start in about 2-3 minutes. We'll give you guys some time to log in and make sure you're all set to go. All right, so hopefully everyone has access to the server now. So the software we're running is, as you guys know, HFSS, but it comes under the ANSYS Electronics desktop. So you can either find it on your desktop, or if you can't, you can search for it from here. So we go ANSYS Electronics desktop. So that's the software that you want to run. So if you've used HFSS before, you may not get this message, but I started on a new server so that I'm going through pretty much the same steps as you guys. So it tells me that a new installation has been detected, and I have to figure something out. Okay, so for the project directory, it's going to default to the C drive, but we want this to be in the H drive so that you guys can access it from any other server. So if you go, if you click here, we want to have the project directory in the H drive. So the H drive will have your name, and that's where you want to store all your projects. All right, so you can create a folder. I'm going to call this ELEC 4503 2020 and A2O. All right, so that would be my my project directory. The temp, you don't really need to change it. You can leave it as is. Yeah, you can leave that as whatever the installation default is. So click OK. And then here, I'll leave this up to you guys if you want to participate or not. And hopefully something happens. There we go. All right, you can close that. All right, so if you follow these steps, you'll see that ANSYS already created a project for you. And if you click on the project and you look at the location here, it should be in the same folder that you created. So this is a project that you can use, but if you don't want to use this project, you can also create a new project. So if you click on new here, you can create another project, and again, the new project will be saved inside in the same directory that you chose. All right, so for now, I will just use the default one that HFSS gave me. So you can right-click and rename the project. So give it a meaningful name. So for us, we can call it the workshop. So lab 1. All right, so the project doesn't have any HFSS design yet, so that's what you need to add. So if you go under desktop, you'll see that there's a bunch of software tools that ANSYS has, and the one that we're going to use is HFSS. If you go under HFSS, you click on the arrow, you can insert a new, yes? Okay, so you, did you guys log in? Okay, I'm just going to go back here and see the chat. So you only have CND. Okay, so if you don't have an H drive, just for now you can save it on the C drive. Okay, everyone that doesn't have an H drive, please send me an email, and I'll figure this out after the lab. But for now, you can save it on the C drive, you will still be able to access it if you log into the same server. So you don't have to worry about losing your data. So you can still save it on the C or the D, as long as you know where it is. So you unfortunately cannot get a local license to your PC. You're gonna have to use a server all the time. Okay, perfect. I didn't know that. Thanks, Adam. So if you guys can do that, yeah, go ahead. You can do it on your local PC. Okay, so if you guys don't have an H drive, so just use a C or D for now and follow along. So I assume that you guys figured out where to go from here. So as long as you have a project somewhere, you can still follow along. Okay, so since the H drive problem, so save the project somewhere, you can rename the project, and we want to add an HFSS design. So hopefully everyone is on the same page. So if you click on that, it should add a design inside your project. And as you guys can see, the solution type is driven modal, which is the default, and that's fine. That's what we're going to use throughout the semester. But if you want to know how to change it, if you go under HFSS solution type, that's where you can change the solution type. But again, that's not something we're gonna need to do, so you can just leave it as modal. Okay, so now this is your this is the space that you're gonna design your model. This is a panel where your models are gonna show up, and this is your project. And inside the project, right now you have one design, but of course you can add other designs as well. So again, make sure you give it a meaningful name so that when you come back to it, you know what it is. Our first design will be a rectangular waveguide. So you can just call it something like that. So the first step in the design, if you guys remember that flow chart from the presentation, is to design the 3D model. So a rectangular waveguide is a very simple structure. It's just a rectangular box. So if you go under draw, you see here a bunch of things that we can draw. You can draw a box, a cylinder, a sphere, a cone, and so these are 3D structures. You can also design 1D or 2D surfaces or polygons as well. So for now, we just need to draw a box, which will be our rectangular waveguide. So if you just click on box, this will give you the option to draw it. So there's a lot of ways you can do this. You can move your mouse and look at the coordinate system coordinates on the left side of the screen. You can go down here and type where you want to start for X, Y, and Z. But in my opinion, the fastest way to do it is to go inside the properties. So when I draw something, I usually just put any shape anywhere in the solution space. Just put a box somewhere. And then I set the dimensions later on. So I will do this again. So I'm just going to delete that. So you go under draw, box, and then you click with your mouse to start. So the first motion will be the 2D plane where you want the box. If you click again, it will allow you to put the height of the box. And for now, it doesn't matter where you start and where you end, just put a box somewhere in the solution space. So throughout the workshop, if you guys think I'm going too fast, just point it out. If I'm going too slow, point it out. I'm just gonna, we'll see where it goes. And if there's something that I think needs to be done more than twice or once or twice, I'll do it. All right, so now you have a box. You don't know what the size of that box is. It's just there. The default material of anything you draw is vacuum if it's a 3D model. So now we have a box. The box material is vacuum, and it's called box 1. So you can change the name of that. You can call it waveguide. All right. So when you click on your 3D model here, you see the properties on the bottom left corner. So the material is vacuum, and we want to design an air waveguide, so you can either leave it as vacuum or you can also change it to air if you want. So I'm going to change that to air. So if I go under edit, I can search for the material that I want. So if you just search for air, then you have air here. You can see the properties, relative permittivity, slightly more than 1. Relative permeability, loss tangent is 0. Air is lossless. So you can select air, and if you click OK, this will change the material of the box to air. And you can also change the color. So I can make it this color. So if you have a lot of designs in your or a lot of parts in your design, you can put them as different colors, makes it easier to see. You can change the transparency. So sometimes you might have two parts inside each other. So if you want to see what's inside, you can make it more transparent. So there's a lot of things that you can control about your model from the properties window here. All right, so this is good, but the most important part, of course, is the dimensions. So right now, if you go under create box, under the properties, you can see the start position, the size in the X direction, size in the Y direction, and the size in the Z direction. So the best way to use HFSS designs is to always define things in terms of variables, because number one, it makes it easier to change later, and number two, you don't have to remember numbers. So everything, make sure you get into this habit, define it in terms of variables. So for the position along X, Y, and Z, let's say I want my waveguide to be in the XZ plane. So I want it to start here and I want it to go along the Y. So I want it to be centered along y, so I can create a variable called waveguide width, and I want it to start at waveguide width over 2. So this will be the x start point. Okay, so you x start point and then comma, and then for y I just want it to be at 0 as a start for y, and let's say for z I also want it to start at z0. So whenever you define a variable, if it's not in your project and you click enter, HFSS is going to ask you, do you want to add a variable? Because we don't know what this is, so waveguide width. All right. For the unit type, you can select the unit type. You can select the unit, but you can also easily just type out what the value is, and HFSS is going to recognize it. So for our waveguide width, we want it to be 15 millimeters. If you just click 15 and then if you just click tab, you can see that it's going to recognize 15 millimeter as a length and the unit as millimeters. So that way you can just type out what the number and the unit is, and then HFSS is going to recognize that. All right, so you can click OK. And some of you might notice that the design just disappears, and that's okay. It's just, it's still there. So if you guys click on Control D on the keyboard, it's going to go to the design right away. So Control D. So make sure you click on the solution space here, and then Control D. That will go to the design. So if I just zoom out. And Control D, that should get me to the design. Okay, so we have a waveguide, we have the create box, then these are the position and dimensions. Okay, so now let's keep going. So for the x size, I want the waveguide width to be the x dimension. So the size in the x direction will be just waveguide w. And again, HFSS will give you options for the variables. So if you see it, you can just click it. So you just waveguide width in x. In the y direction, that would be the length of the waveguide. So we can create a new variable called waveguide length. And again, HFSS will ask you what's the variable, and it's going to maybe suggest something, but we actually want it to be 10 centimeters. So again, you can click 10 and then cm, and then it's going to recognize it as a unit, and then OK. And then for the z direction, we want that to be the height of the waveguide. So you can click, you can create a new variable called waveguide height. And here we want the height to be 7 millimeters. Okay, so now you have a waveguide. Again, if it's just filling your screen, you can press Control D, and that will show you the whole design. So right now, everyone should have this design. Let's say you made a mistake in the value of the variable. If you click on the project, you can see all the variables here. So create box. So these are the variables. I'll let you guys take a look at them. So we have the width 15 millimeters, the length 10 centimeters, the height is 7 millimeters. And then under create box, that's everything that I defined. So I'll give you guys a moment in case you want to copy that. And what's neat about having variables is you can always change it and you don't have to go back to the design. So if I want to make the waveguide shorter, if I just type 5 centimeters, it will just shorten the waveguide, which is really helpful if you want to run some sweeps of variables. So you don't have to go into the design and do it manually. So we can make that 10 again. Okay, so the rectangular waveguide is a very simple design, and we have finished the first step. So the first step from that flowchart was to draw the 3D model of the design, and we're done. We drew the rectangle. The second step is to define boundaries. So right now, this is a vacuum box, and HFSS doesn't know what the boundaries are. So if you don't define boundaries in HFSS, it's going to assume that everything around this box is a perfect electric conductor or a PEC. And what I mean by everything, I mean the edges of this structure. So the edges are all the faces. So if you click F on the keyboard, you'll be able to select faces, or you can also right click and go under selection mode and click faces. So either F or right click. What I mean by boundaries again is these faces. So these faces of the structure, everything you don't define as a boundary, HFSS will assume that it's a PEC, a perfect electric conductor. So that's something you have to keep in mind. And right now for rectangular waveguide, we are lucky because we want the four faces of the rectangular box to be perfect electric conductors because it's a rectangular waveguide. But we can also define them as copper if we wanted, and that's what we're gonna do. So we're gonna define them as copper, but if we don't, we would still be okay because HFSS will assume that they are perfect metals. So let's go ahead and define the faces as copper. So again, if you press F on the keyboard, you'll be able to select the faces of the structure. All right, so I'll select all the faces together and then define them as copper. So if you select this face and then if you control on the keyboard, you can select the second face. And then you can click on rotate. I want to be able to reach the other faces, so you can rotate the structure. And then you have to press F again if you don't have a mouse like me. And then control. And we have one face left, so the bottom face. Press F again and control F. Alright, so everyone should have selected the faces of the waveguide. So every face except the two small rectangles on the end should be selected. And once you have them selected, if you right click, assign boundary, and finite conductivity. So again, right click, assign boundary, finite conductivity. So the default view, if you press Control and then D on the keyboard, you'll be able to get to the full view of your design. Okay, so assign boundary, and as you guys can see here, there's a lot of boundaries that we can assign. The most popular one is the perfect electric conductor or perfect E. But again, if you want something to be a perfect E and it's at the edge of the solution space, HFSS will just by default assume that it's a PEC. But you can also define a perfect magnetic conductor, perfect H. You can have impedance boundaries. You can have so coupled boundaries are like primary, secondary boundaries. We're not going to use those, but you can see we have a lot of options here. We want to define copper as the boundary. So if you go under finite conductivity, you can manually enter the conductivity that you want, which is in Siemens per meter. But we can also just say use material. If you click on use material and you click on here, you can search for copper. And there it is, and you can see the properties of copper. So the conductivity is really high. So if you click OK, and you click OK here, that means the faces we selected are now defined as copper. And if you go under boundaries, so if you go under the HFSS project and then boundaries, then you'll be able to see finite conductivity, and that is it will show you the surfaces that we selected to define as copper. And again, you want to make sure that the waveguide is only the 4 faces are selected as copper, because the other 2 will be selected as excitations, and we'll see that in a second. Sorry, say that again. Okay, tell me. Oh, okay. If you go under orient, if you do like isometric, or try other like trimetric, or you can rotate. So let's say it's shown like this. If you click on rotate, you can move it around. And if you have a mouse, you can I think you can just click on the solution space and move it. But clicking on rotate will guarantee that you can move the model. Whoever asked the question, can you just confirm that you can do that? Okay, perfect. Okay. I'll slow down like when I'm... Okay. Alright, I will do the finite conductivity part again for everyone to follow. So you were saying that when I rotate the model, things are choppy? Oh, okay. Okay, I'll do it again. So I will delete the boundary that I just set. So now we're back to selecting the boundaries. So we want to select the 4 faces of the waveguide that I just showed you guys before. So you can just select, like if you press F on the keyboard, or go under right click, selection mode, and faces. Then you'll be able to select faces. So you can select the first face, and then if you press Control, that will allow you to select multiple faces at the same time. So if you press Control, you can select the second face, and then you can rotate the model so that I can see the other faces. I can do that. So these 2 faces are left. If I press F again, I can Control F here. Not Control F, just Control and click. So what you want is the 4 faces of the waveguide to be selected. And you can always change the orientation that it looks a bit nicer. You can Control D to see the full structure. And once you have these faces selected, you right click, assign boundary, and finite conductivity. And inside finite conductivity, you can even give it a name. You can say like waveguide faces. Yeah, you can give it that name. You can use, so we want to select the material as copper, so you can select use material and then search for copper. And then once you have copper selected, you click OK. Already a project definition with the name copper. Okay. I don't know what happened there, but you can just select copper, and then OK. So now you've defined the boundaries of the waveguide as a finite conductivity, and it's copper. All right. All right. So hopefully everyone is caught up. So we have finished the second step, which is okay. So in order to do that, if you're under the project, you have the HFSS design. If you click on the plus sign here, you'll be able to see the properties of this design. And under the properties, one of them will be boundaries. If you've already defined a boundary, you should be able to see it here. He can't select all the boundaries? Okay, so just for the rectangular waveguide, because HFSS will assume that the surfaces that we don't define are pecs. You don't have to define a boundary. So all I did is I just wanted to show you guys that you can define a boundary as copper, but since copper and perfect electric conductor is pretty much the same, you don't have to worry about defining a boundary now. As a matter of fact, I can just delete it and it would still be, you would still be able to follow along. Okay, perfect. All right, so again, the boundary that I just added is copper. If you cannot select the faces, that's okay, because HFSS will assume that it's a PEC anyway, and that's close enough. All right, so the second step is done. The third step was to define excitations. So now we have a structure. We've defined the boundaries. Now we need to tell HFSS where the energy is going to come from and where we want to receive that energy. And as you guys know, for a waveguide, the ports would be these ends of the waveguide. So if I just select the escape, I don't want to select the boundary. There you go. All right, so for the waveguide, it will be this face and the opposite face. So these will be our ports, and that's where we're going to define the excitations. I'm gonna start by defining this face here. So if I just rotate the structure, just play with it a little bit, I can select this face. So this face, we want to define it as a port. So if you select the face, if you right click, assign excitation, wave port, click on that. I will do this again just to make sure everyone is caught up. So if you select the face, if you right click, assign excitation, and wave port. Oh, my mouse is a little weird. Okay, assign excitation, wave port. So the name, you can just leave it as 1. Number of modes, this will be important for waveguides. So as you guys know from 3909, that in a waveguide there's more than one mode that can be excited. For now, we're only interested in the fundamental mode. So if you set the number of modes as 1, it will only excite the first mode, which is okay, so we can leave that as is. The integration line, we're not going to use yet. What the integration line tells HFSS is in what direction to apply the electric field, but for now we can just let it decide how to apply the electric field, so that's okay. You can leave that as none. So you can click next. Over here we have the port renormalization, and this choice here is important for your design. So the first choice is do not renormalize. And what that means is your port impedance will take the same impedance as the transmission line that you're connected to. So if you're connected to the waveguide, it will take on, in this case, the impedance of the fundamental mode. If you're connected to a microstrip line, it will take on the impedance of the microstrip line. If you say renormalize, you can fix the port impedance to a certain value. And that could be important if you want to check the reflection from a certain transmission line, and you know that when you physically have the structure, you can have a 50 ohm connector. But for now, we want to say do not renormalize because we don't know what the input impedance of the waveguide is. When we don't renormalize, we can actually check the port impedance that we have. So for the microstrip line, which we're going to do next, we're going to be able to see what the characteristic impedance of the line is. So for now, we can leave that as don't renormalize. De-embedding is another option. If you want to take your S parameters at a certain location inside the structure, you can de-embed, but we can leave that as don't select it. Okay, and once you click on finish, under the project, the design, you should be able to see the excitation over here. All right, so let's do that for the other port. So we can go under here. I can select the face, and I can do the same thing, assign excitation, wave port. So this will take on, number 2. You can leave everything the same, and again, don't renormalize. And now you have the 2 ports. So you have port 1 and port 2. Now, how do you know which one is being excited? Because you can excite either this side or this side, or you can try exciting them both at the same time. To know what you're actually exciting, if you click on excitations, if you right click and you go and edit sources, you'll be able to see which port actually has a magnitude of excitation. So right now, by default, port 1, which is the first one we assigned, will be the one which is actually exciting the structure. And we're here exciting it with 1 watt. And you can always increase that to any other number. You can change the phase at which the excitation is starting. And you can also change, instead of exciting port 1, you can excite port 2. And we'll try that later on when we look at some results. But for now, you know where the excitation is being applied. So if you right click on excitation, edit sources, you can see exactly which port is the one that's sending in the power into your waveguide. Okay, so we've defined the excitation. The next step is to create the solution setup. So we want to tell HFSS what frequency to solve this structure at, and we want to define some convergence criteria. So I'm going to go over this slowly. There's going to be some numbers we're going to put in, so we'll make sure that everyone is caught up. So under analysis, if you right click, you go add solution setup, and let's do the advanced choice here. So analysis, right click, add solution setup, and advanced. Okay, so let's look at the options that we have. So the solution frequency, you can either define a single frequency, which is what we're always going to do. You can define multi-frequencies or broadband. What the solution frequency is it's going to determine how fine the meshing is. The higher the frequency, the finer the mesh of your design is going to be, but also the longer it's going to take. So the frequency that you want to select in order to get good accuracy, but at the same time run the simulation in a manageable amount of time, is the maximum frequency that you're interested in, or maybe a little bit higher than the maximum frequency you're interested in. So I know what this waveguide response looks like, so I know what the cutoff is when I designed it. So what I'm going to do is I'm going to select a frequency that's higher than the cutoff so that I get some accurate results. But sometimes you may not know what the best solution is. So when you're designing something that you're not familiar with, you might choose a frequency and then look at the results and then maybe increase the frequency a little bit, see if the results improve or change. If they change, that means your solution frequency is, your results are sensitive to the solution frequency. If they don't, that means the solution frequency is fine. So for our design here, I will select 15 gigahertz as the solution frequency. So that means here, if I select 15, if I want to look at the results at 20, I should be careful. I shouldn't trust them that well, because 15 is less than 20. But if I'm interested between, let's say, 1 and 14 or 1 and 15, then the meshing should be good. The next option is the maximum number of passes. So HFSS has an adaptive meshing process. So what it's going to do is going to mesh the structure a certain way, and that will be the first pass. And then it will mesh it again a second time, calculate the results, and then see if the results change a lot. If they do, then it will do another pass, make the meshing finer and finer, until the results don't change that much, and then it will stop. But of course, you need to set a limit to how many passes it can go, because it can go forever, but we don't have forever. So maximum number of passes, depending on your design, you might want to go 10 to 30 passes. For now, we can choose 15 passes. So that means that HFSS will try to get the conversions within 15 passes. If it's successful in getting it under 15, then it will just stop. So it can get it from, it can do 3 passes, 5, 6. But if it gets to the 15th path and it doesn't converge, then it will just stop. The next parameter is the maximum delta S, and that is the convergence criteria. So that's a very important number. So the maximum delta S is the maximum change in the S parameters from one pass to another pass. So if the S parameters change a lot, that means the solution hasn't converged, and you want HFSS to go another pass. And you set this criteria. You tell HFSS at what point or what is the maximum value of error that you accept in the design. The default is 0.02, but 0.01 is usually acceptable. If you want really strict requirements on your accuracy, you might want to go 0.001. But in most of the designs that we're doing, 0.01 is good enough accuracy. So for the maximum delta S, 0.01 is good. So you can set that as your maximum delta S. All right, so this is the first screen that we're gonna set the options at. The next one is called options, and here we're gonna define even more convergence criteria. So by default, if HFSS converges, and what I mean by converges is if the maximum delta S between 2 passes is less than or equal to 0.01, it's going to stop. So it only needs to get that once. But under options here, you can tell HFSS to run a certain minimum number of passes, which means even if it converges after 2 or 3, you might want to run it for at least 6, just to really make sure that it converges. By convention, we usually say like 6 minimum number of passes. So what you want to do is you want to make sure that the meshing is good. You run it 6 times. HFSS is happy with it, and then it can stop after that if it does converge. Another requirement for conversions, which makes it even stricter, is the minimum converged passes. So by default, if HFSS converges converges once, then it's going to stop the simulation. But you can say that I need you to converge 3 times. And this would be 3 times in a row. So this really makes sure that the results do not change for 3 consecutive passes, and that again will set the requirement for your conversions higher. Okay, so once you're done 6 and 3, and again these are numbers that I found to work in almost all cases, but you may want to play with it and see what you get. You can set the minimum number to 6 if you wanted, but 3 works well enough. And that's it. That's all we need to change. So if you just click OK, then it's going to take you to the frequency sweep. And just for the first time doing this, I'm going to run an interpolating sweep. And as you guys know from the slide, there's 3 types: discrete, interpolating, and fast. Discrete is the most accurate, but also takes a long time. Interpolating is like halfway in between, and I'm going to choose that for now so we can look at some results. For the frequency sweeps, you can define linear count, linear step, log scale. For now, we can just leave it as linear count. The start frequency, let's say, let's do 1. Let's do 5. Let's do 5 gigs to 15. And number of points, you can select 4 or 1. I find that the number of points doesn't really affect the simulation time for interpolating. It does a little bit, but not as much as discrete. So for example, you don't want to run 401 points on discrete. You don't want to do that because it's going to run the simulation 401 times. So if you want a lot of frequency points, your best bet is to go interpolating or fast. If you want the solution to be very, very accurate at like 5 or 6 frequencies, then you can do discrete. But for now, interpolating 401 points is okay. And then you can click OK. So under analysis here, you should be able to see your setup, and you should be able to see the sweep that we just created. And if you want to change the sweep parameters, you can do that if you just click on sweep. So the start and stop are 5 and 15 for 1 points, interpolating, and so on. Okay, so hopefully everyone is good to go. So once you've defined the frequency sweeps, you're pretty much done. You just need to validate and simulate. So if you go under simulation, validate, this HFSS will just go through a checklist, make sure you designed the model, the boundaries and excitations are set, you've defined the mesh and convergence criteria, you have some sort of solution or frequency sweep. Optometrics, we don't have any, and we don't have any radiation yet. So it just makes sure that you've designed the model correctly, so you can close that. And then when you're ready, you just click on the design and then click on Analyze All. So this will start the simulation. And over here you can see the progress. If you click on Show Progress, so you can see HFSS going through the passes. So pass 1, 2, 3, 4, it's solving it. And remember, we set 6 minimum passes, so it has to do at least 6. Going through the sweeps. Okay, so my simulation is done. It might have been might take longer for you guys, but let's see. I'll wait a few more minutes. Could I go over it again? Okay. Go over which part, Ryan? What do I need to hit before validate? Okay, so if you when you click validate, okay, so I'll go for this again. So if you've already set your solution setup, so over here, so if you right click on the setup or you just double click on it, if you've already done this and you've set your convergence criteria and you've set your frequency sweep, so the interpolating and the number of points, once you click on validate, you just want to make sure the design is good, and if it's good, then you just analyze all. So validate, analyze all. So analyze all will just run the simulation. Okay, I think you got it. Okay, so this was supposed to be a very small simulation, so I think everyone should have gotten their simulation to finish. If your simulation is still running, just send a message and I'll wait for it to be done. No, when it's done, it's just going to stop. We're gonna check the conversions in a bit, but yeah, when it's done, it's just done. Okay, so so sometimes, like if you click on messages, if something went wrong in the design or the simulation, you might be able to you will be able to see it for sure. So here it just tells you that it's done interpolating. You don't have to check this every time, but just so you know, like if you're running something and something goes wrong and you need to send me an email, a lot of times the error will be down here. So if you just send me a screenshot of that, I might be able to debug the problem that you're having. But this was a simple simulation and it ran well. It tells you here that it's converged, but again, we're going to check that in a better way, and it finishes simulation. All right, so how do you check the convergence? So that's the first thing that you guys want to check every time you run a simulation, and for the first few reports, I will ask you to include the convergence plot, which I will show you in a second. So if you go under results and you click on solution data, and you click on conversions, so that's where you make sure that the design has converged. So you can see here that well, it's converged, right? The target is 3 consecutive converges, which is what we said earlier. We converged 5 times, so we exceeded the expectations. The maximum delta S, which you can think of as the error, is well below the convergence criteria that we set. So if you guys remember, we set 0.01. This one is well below 0.01, so it's done really well. You can view these results in a plot instead of a table, and over here you can see this is where we set the conversions, the limit for the convergence, and we have converged almost for every pass. So what you can do is you can say, okay, maybe I want it to be even better, so you can set the conversions here, but that means it's going to run for longer in order to meet your 3 consecutive passes criteria. So in the report, when I ask you guys to show me the conversions, you either show me this plot, so you can just take a screenshot of that, so I want to see that your design has converged based on your criteria, or you can just show me a table and I can see here that the maximum error is well below what you set. So that's the first thing you want to check right after the simulation is done, because HFSS will not give you an error if it doesn't converge. It will not. It will probably tell you down here that it hasn't converged, but that's something that you have to check yourself. Okay, so once you know that it has converged, now you can start looking at some results. One thing we can look at is the S parameters of this design. So if you guys are familiar with S parameters, they are network parameters. They can tell you the reflection and the transmission in a device. Right now, this is you can think of the transmission line with the waveguide as a 2-port network. So we have port 1 and we have port 2, and we want to see the scattering parameters of these two between these 2 ports. So to do that, we look at the results. So there's a results part here. If you right click, you go under create modal solution data report, and as you guys can see, there's a lot of options. You can look at the Smith chart results, you can look at data table, you can look at a 3D polar plot, but a lot of times a rectangular plot is usually good in representing S parameter data that we want to look at. So if you right click on results, create modal solution report and rectangular plot, that will give you this window, which shows S parameters that we can see. There's also other parameters that we can check as part of the results, like Y parameters or Z parameters, or the VSWR, the port Z0, which is the impedance of the wave port. And we'll look at that in another design. But for now, we want to look at the reflection and the transmission. So that would be S11. So S11 is the power at port 1 relative to the power that you put in. So if there is no reflection, you shouldn't be getting anything back. S21 is the transmission between port 1 and port 2. So in any waveguide system, we want the maximum power transfer from port 1 to port 2. So ideally, we want low reflection and high transmission. So right now, let's plot these two. So if you just control, you can select these two. So S11 and S21. Let's plot them in dB. The solution here, we only have. So we have the last adaptive is 1 frequency point, and it's your solution frequency. The sweep is your frequency sweep. That's the interpolating sweep that we set earlier. And the trace will be a function of frequency, and we want to plot S11 and S21. So you guys can play with this later on, but for now the default values are okay, so we can work with that. So S11, S21 in dB, and you can create a new report. And we can close that. And over here you can see we've plotted S11 and S21, and as you guys might have expected, the waveguide has a cutoff frequency, and it's exactly 10 gigahertz. So the S21, the transmission is low. There is no transmission down the waveguide. The waveguide is in cutoff. Once it hits 10 gigahertz, then you start having a transmission down the line. The reflection is low when there's transmission, and over here there's no reflection, but there are evanescent modes, if you guys recall rectangular waveguides. So that is an expected S21, S11 plot for rectangular waveguide, where you have the cutoff region and then above the cutoff region. Okay, so that's one result that we can view for the waveguide. Another thing we can do is look at the fields inside the waveguide. And if you guys remember, interpolating sweep does not give you, it doesn't solve for the fields. So for that we need to add another sweep, and for that let's choose a point inside the propagating region here. So we can pick let's say 12 gigahertz. So we want to add a discrete sweep, because a discrete sweep can give you the field solution, and we're going to add it at a single point. So remember, a discrete sweep, you don't want to run it at a crazy number of frequency points. Just a handful of frequency points is okay. So if you go under setup, if you right click, you can add a frequency sweep, and that one we wanna have a discrete sweep, and let's say a single point, and I think we picked 12, so 12 gigahertz, and you want to save the fields if you want to see them. So you can select save fields here, or you can just do it here. So either way is going to save the fields. Alright, so we're just adding another sweep, and it's a discrete sweep for 12 gigahertz. And if you add a frequency sweep after you've already solved your design, you have to run the simulation again. Makes sense, because it hasn't solved it yet. So if you click OK, so two things you can do here to run this. You can right click specifically at the sweep that you want to run, and you can say analyze, or you can also say analyze all, but since it's already solved for that, it's just gonna do one simulation for this. So you can just right click and say analyze. And since this is a single frequency point, it shouldn't take that long, even though it's a discrete, and it's very accurate. So you can see here it's solving one, and it's all done. So I'll give you guys a minute or two in case some people are still doing it. So the numbers for the second sweep, it was just a single, I'll show you here. So it was a discrete, and it was a single point at 12 gigahertz, and you want to make sure that you save the fields. Okay, so let's look at some fields. So we want to see the fields inside the waveguide. So in order to do that, you can click on the part that you want to solve the fields inside, or not solve because the fields are already solved, that you want to plot the fields inside. So if you right click on that, you can say plot fields, and here you have options for what fields you can plot. You can plot the E field, H field, the current, quality factor, and other stuff. For now, let's plot the E field, and let's plot the magnitude of the E field inside the waveguide. So you get to this window. So there's going to be two. One thing that I forgot to mention at the beginning is the solution frequency that you set at the very beginning. By default, HFSS will solve the fields at that frequency. So if you guys remember, we set the solution frequency to 15. By default, there is going to be a field solution at that frequency. But now we want to look at the other discrete sweep that we had. So that was sweep 1, and that's where you can see the 12 gigahertz that we selected earlier. So from here, you can select discrete sweep, and then the frequency that you want to, where it's the only frequency available. And we want to plot the magnitude of the E field inside the waveguide. and done. So you guys should be able to see here that this is the fundamental mode inside the waveguide, you might have seen this before in 3909. And you can see so that's the magnitude of the field propagating down the waveguide. It's a neat plot. You can also plot the H field. And one thing you can do as well is you can animate this field. So you can see how the field propagates down the waveguide. So if you go under field overlays, you can find the magnitude of the field that you just plotted. If you right click on that, you can animate. So if you animate, you can leave this as is, and you can click OK. So over here you can see the propagation of this field down the waveguide. And if you guys notice, you can see where the power is coming from, because we set the power to be coming from port 1, so that's where the excitation is, and as you can see, it's getting fully absorbed in port 2, which is what we expect. The transmission is really high, so that's the field. But what happens if we change the excitation to this side? So you would expect the field to go the other way. So let's try that. So we can close the animation. So if you guys remember from excitation, you can change the side to which you apply the port. So if you right click, edit sources, instead of exciting port 1, we can excite port 2. So I just moved the power of 1 watt from one port to the other. Okay. And the thing about changing the excitation is you don't have to run the simulation again, because it's already solved the fields inside, and changing the side of the excitation doesn't mean that you have to run it again. The solution is still there. But now if you animate the fields, if you go under animate, you can see that the power is going to come from the other side, because now we're applying the 1 watt from port 2 as opposed to port 1. Okay, so that's the end of the waveguide demo. We're going to move on now to the microstrip line. Just give you guys a few more minutes to save the design. So after you're done, and actually not after you're done, make sure you always save the design as you go along. Just make sure you don't lose your data. So if you just click on the design or on the project, you can click on save, and that will just make sure that the design is saved for you. Could I show how to animate again? Yeah, I can do that. So if you already have the fields, you can find the field under field overlays, E field, and then once you find the field, you can right click, animate, and here I've already had the animation from before, but if you didn't have it, you will get to this window. So you can just leave the default values for phases, and you can just click on OK. You can increase the speed of the animation. And you can also export it to a video file, I think. Yeah, you can export the animation if you want. But yeah, that's how you get to the animation. Hopefully that answers your question. Yeah. Okay, so if you have the design saved, that's good. Make sure you save it. So now let's move on to the microstrip line. So to create another design, you can go under desktop, HFSS, and you can click that again. All right, so we have a new design inside our project. So we're still in the same project. We just created a new design, and that one will be the microstrip line. So we can call it microstrip line. and the default is driven modal. That's good. Okay, let's start. So again, thinking of that flow chart to just help you to get the steps in. The first step was to design the model. So for a rectangular waveguide, that was a simple box. For a microstrip line, we have at least two parts. We have the substrate, and we have the line on top of the substrate. So two things that we have to add. So let's start with the substrate. So a substrate is simply it's a rectangular box. So you can just go on box again. And again, just like last time, just put a box somewhere. Okay, so we have the box. Maybe give it a nice name and call that substrate. Substrate, that's right. A new model in the same project. So this is the project. If you want to make a new design in your project, you go under desktop, and then under HFSS, and then click on HFSS. That should create a new design in your project. And that's what I did to get that one. Okay, so once you get to the design, you can add a box. So if you click on that, and then you just select 3 points, put the box somewhere. I just renamed it from box 1 to substrate. So the material, so the substrate that we want to use for this microstrip line is FR4. So if you click on here, you can go under edit, and you can search for FR4. So if you search for FR4, that's right here, FR4 epoxy. And you can see the relative primitivities. That's epsilon R, it's 4.4. The two important parameters that you should pay attention to for substrates is the relative permittivity and the loss tangent. So the loss tangent here is 0.02, and FR4 is one of the more lossy substrates. So 0.02 is relatively high for a substrate, but it is the most used substrate for a lot of the transmission line work, especially for demos and stuff like that. So once you have FR4 selected, you can click OK. So now this box is an FR4 box. The next step, you can change the transparency, or you can change the color. It's up to you guys. I'll just leave it as that. Okay, so once you have the box, you can now set the dimensions. And just like before, we're going to use variables. You guys are pros at this. So first variable, I would say, let's call it sub width over 2. So I want it to be centered. And this is what you will notice is a lot of the designs I make are centered around one of the axes, and that's why the position I set it as the variable over 2, and then for the size I set it as the variable. So this just makes it centered. So for the x position, I'm going to set it as the substrate width, and let's say y and z, I'm just going to start at 0 for both of them. And again, new variable. I think that one, it was 50 millimeters. So the width of the substrate was 50 millimeters, so 50 mm. Again, it's going to recognize length. And don't worry if it disappears, it's going to come back, we'll bring it back. The size in the x is the substrate width, so you can just type that. Let's say it's a square substrate, so the size in x and y is the same, so just the substrate width here as well. And the height will be the substrate thickness or height, so create a new variable called sub h, and that one, is 1.27 millimeters. So 1.27, I chose that. It's actually in mils. I can't remember if it was 10. It's some number in mils. That's the standard thickness for a substrate. That's why I picked that size. But I wrote it in millimeters, but you can also write it in mil. So if your substrate is 10 mil, you can write 10 MIL and it will recognize mil. But for now, I'm just working in millimeters. So 1.27 millimeters. Okay. So again, to view the whole thing, you do Control D on the keyboard. You can see the whole substrate. And just remember, the variables are set over here. So if you click on your project, you can see the variables that you've designed. So if you made a mistake in writing one of the numbers, you can always come here and fix it. So these are the width and height of the substrate that I chose. And over here, those are the positions and X, Y, Z values. Okay, so one down. We've designed the substrate. We've chosen the right material. The next step is to design the microstrip line or create the microstrip line on top of the substrate. So over here you have two options. You can either create a rectangular box with a certain height, or you can create a 2D rectangle for the line. Since we're operating at fairly low frequencies, the thickness, since it's going to be small anyway, we can just choose a 2D surface instead of an object. And since we haven't done that yet, I'm going to use a surface instead of an object for the line in this case. But just so you know, you can also choose a trace with a certain thickness, which is of course more realistic in a real life application. Okay, so in order to create the line, under draw, you want to create a rectangle. So that's a 2D surface. So if you click on that, just like before, it doesn't matter where you start. We'll just put it somewhere and then we'll fix its dimensions later. So you can just put a rectangular surface somewhere. And as you can see here in the model, it's not a solid, it's a sheet because it has zero thickness. So it's a sheet with zero thickness, and since it's a sheet, you can't really assign a material to a sheet. You assign a boundary. That's why it says here it's unassigned, because you haven't defined what this boundary is. And of course, for a microstrip line, it's going to be copper as the boundary or the material, but it's not really a material because it's not a solid. All right, so if you click on the rectangle, again, give it a meaningful name. You can call it the microstrip line. And just so that we can see it, I'm going to give it a different color. So I'm going to give it color orange so you can see it on the surface. Okay, you still can't see it because it's hidden, but we'll bring it up. All right, so for the position, the line will have the same length as the substrate, and the width of the line will be something that we assign. So let's get started. So for the width of the line, we can start creating a variable called microstrip width over 2, because we want it to be centered. We want it to start at 0 in Y and 0 in Z. And I have calculated that for 50 ohms, the width of the line needs to be 2.43 millimeters. All right, so microstrip width is 2.43. Now, for the X size, so the X size will be the width of the line, so that we can just write the same variable that we just created, microstrip width. For the Y size, it's going to be the length of the substrate or the width of the substrate, so sub width. And I made a mistake here because I defined the position to be at 0 in X, but we actually want it to be on top of the substrate, and the substrate height is sub H. So we have to start at sub h not 0. So sub h. Click on that, and there's the line. So again, the variables are under here. So the only variable that I added is the width of the line, which is 2.43 millimeters. And if you go under, you might have to click rectangle, create rectangle, you'll be able to see the position and the length of the line. And here you can see that creating a variable is again really nice, because if I change the width of the substrate, if I make it shorter, the line will follow along, and it's just a lot nicer than having to do it manually. So you can just fix that back here. All right, microstrip line, got the dimensions. Hopefully everyone is caught up. Okay. So right now we have the next step is to assign the boundaries. All right. So the first thing that we don't have a boundary for is the microstrip line, and that it would just be copper. So if you select it, right click, assign boundary, you can assign it as finite conductivity, just like we did before. You can use material and choose copper. You select copper here. I don't know why I get this error, but anyway, it will just select copper. Click OK, and under the project, if you go under boundaries, you will be able to see the transmission line defined as copper here on top of the substrate. All right, so that's one boundary down. Now the other boundaries is not as clear as the rectangular waveguide, but if you guys think about it, we have the substrate, the top, we have the copper trace, the bottom, we want it to also be metal, so that's another boundary that we have to define. But for now, just to show you guys that it works, I'm going to leave it undefined, the bottom part, because again, HFSS will assume that it's a PEC, and a PEC is close enough to a copper, so I'm not going to define it. So I'll just leave it undefined. So the other boundary, which is not very clear, is the top here. So we want the top boundary to be open, right? It's going to be a transmission line. We want this to be open. So in order to have an open boundary in HFSS, you have to define a radiation boundary. And to have a radiation boundary, you need some sort of a radiation box around your design space, or around the substrate here. So another object that we have to create, which is not really a physical object, but it's something that we need to create to solve this structure, is another box, and define that box as a radiation boundary. All right, so what we can do is create another box. So again, you don't have to start somewhere specific. You can just create the box somewhere. And this radiation box, it has to cover the substrate and be a little bit higher than the substrate so that there is air. So it's to be an air box or a vacuum box. So you can call that radiation box. And you can leave it as vacuum. I'm gonna make it very transparent so that we can see inside it. You can choose the transparency a little high, so you can see inside it here. And for the size, so we want it to be the same size as the substrate. So you could, in theory, make it larger, but you don't have to. For now, we'll just make it the same size as the substrate. So we'll go minus sub, same size in the XY plane, I mean. So we can go sub W over 2, 0 and 0. And the X size will be sub W. Y size will be, again, sub W. And for the height, so usually what you want is you want it to be at least like a wavelength away from the line. So for now, because we haven't discussed anything to do with frequency yet, I'm going to define it as, let's say, 20 times the height of the substrate, should be okay. So I'm just going to say 20 times the height of the substrate. So these are the dimensions of the radiation box. There is no new variable created. It's all based on the substrate. I'm just going to go Control D here so you can see the whole thing. So far so good, hopefully. So now we've created a box which we have to define the radiation boundary on. So now the radiation boundary would be all the faces around and on the top. So the bottom face will be the trace, sorry, not the trace, the ground of the substrate. And by default, HFSS will take that as a pack, which is good. Now we need to define the 5 faces, so the 4 around and the top, as a radiation boundary. And for that, so you have to do the same thing that we've done before. You're going to have to click F on the keyboard so that you'll be able to select faces. And we want to select the 4 faces around and the top. Face, and then Control, select the other face. You might need to, I think I lost it. Okay, do it again. Face, Control another face, and then I want to rotate it. Just rotate around, and then select this face, and rotate some more. Yeah, if you have a mouse, this is a lot easier than what I'm doing, but still doable. And then select this face, and then finally the top face. So I've selected the 5 faces except the bottom one to be radiation boundaries, which I will do in a second. So once you have all the faces selected, you can right click, assign boundary, and radiation. And here there's no choices. Radiation is basically just open to air. Okay, so I'm just gonna do that. So I have everything defined as radiation except the bottom one. Did I make a new thing in the same project? Sorry, I didn't see that question. Okay, so are we submitting these? You're not submitting these. There is no report for this lab. I'm just showing you how to use HFSS so that you can get familiar with it. I think what I'm going to do is I'm going to upload the HFSS files for this project, just because it's the first one. But I'll let you, in the future labs, I won't be uploading them. But for this lab, I will upload these files so you guys can see what I've done. Okay, so now you have all the boundaries set. The next step is to define excitations. Now, it's a little bit tricky for a microstrip line because what we need to define a port that covers the line as well as the ground. So if you guys know, from a physical perspective, if you have a connector connected to the microstrip line, the center pin is connected to the trace, and then there's also a ground that's connected to the bottom. So we need to define a wave port that covers the line as well as the ground, and it has to be on both sides. One way to do it is you can define this whole face as a radiation as a wave port. So you can select the whole face and define it as a radiation select the whole face and define it as a wave port. And in case you're wondering, this face is a radiation boundary. The priority goes for ports. So if you define a radiation boundary and a wave port on the same surface, HFSS is going to say the wave port takes precedence over the radiation boundary. But that's not what we're going to do today. I want to show you guys how to do it using actual surfaces. But just so you know, it's an option. The only thing is the wave port has to be big enough so that it covers the whole line and a little bit outside the line so that you can capture the fringing fields. If you guys remember, the microstrip line has fringing fields on either side, so the port has to be large enough to cover the fringing fields as well as the line and also touch the ground. So instead of defining this whole face, which is the easy way around, let's create surfaces and define them as wave ports. Okay. All right, so to create a surface, so we've done this before, so you can go under rectangle, but we want the port to be in the X, Z plane. So right now, if you click on rectangle, it's going to be in the XY plane. So if I click here, it will only allow me to put the rectangle in the XY plane, but that's not what I want. I actually want it in the XZ plane. So I want it to be in this plane. And just like every other design we've made so far, you can just put it somewhere and we'll take care of the dimensions later on. All right, so I'll just switch this to XY plane because it's just easier to look at. Okay, so we have a Control D. Orient, so under Draw, Orient, Isometric. No problem. All right, so we have a 2D surface, and we can call it, this is going to be our wave port, so we can just call it wave port. Let's call it 1, because there's going to be 2 of them. All right, so this wave port, like I said before, it has to touch the ground, so it has to touch the bottom of the substrate, it has to touch the line, and it has to be big enough to capture the fringing fields. So a good rule of thumb when placing wave ports in HFSS is to design the width of the wave port to be 6 times the width of the line, and the height to be 6 times the height of the substrate. All right, so when I define here the dimensions, you'll see what I mean. So for the starting point, just like everything else, we want the width, the wave port to be centered. So we'll choose, we'll create a variable. We'll call it wave port width over 2, and for the y equals 0 and z equals 0. Now the wave port width has to be 6 times the microstrip width. Okay, so 6 times the microstrip width. And X size will just be a wave port. And Z size, so Z size will be the height. It has to be 6 times the, no, let's create a new variable. We'll call it wave port height so that we can, we're staying consistent. 6 times the substrate height. And this creates the wave port right here, centered on the line, and it's big enough to capture the fringing fields that we talked about. Okay, so right now it's not a wave port, it's unassigned, it's nothing yet. And by the way, if something is unassigned, if you solve with HFSS, it's just gonna assume it's not there because it's nothing. Okay, so you have a wave port, and I'm just gonna go over the position again. So if you guys missed it, so the width of the wave port is 6 times the width of the line. The height is 6 times the height of the substrate. And just to show you guys that it's actually touching, you know, I'm just gonna give it another color. You guys can see it, so I'm just gonna give it that color. So you can see here that the wave port is touching the bottom as well as the line, and it's big enough to capture both. Okay, go back to isometric view. And once you've created it once, you can just copy and paste. I don't think I've told you this before, but you can Control C, Control V in HFSS, or you can right-click, edit, and copy. And then if you go on the solution space here, you can paste. So it just creates another one, and that one we want it to be on this side. So the only change really is just the Y dimension, which will just be the size of the substrate, so substrate width. So now we've created the two surfaces which we will define as wave ports. So if you didn't get that last part, I'm just going to go over it again. There was no wave port 2. I just copied wave port 1 and paste in the solution space, and then I changed the Y dimension from 0 to sub W, so that it just moves on to this side of the substrate. Okay, hopefully everyone has got the two surfaces, and now it's time to define them as waveports. So just like you've done before for the waveguide, if you right click, you go under assign excitation, waveport, and you guys, so the number of modes doesn't really apply here, we can just leave it as 1. And again, you can set the port impedance, but we want to actually see what the transmission line impedance is, so I'm just going to leave that as don't renormalize. So basically you don't have to change anything in the settings. So you do that for the second one as well. Assign excitation, waveport, and alright, so under excitations you should have port 1 and 2. Under boundaries you should have the finite boundary for copper, which is the line, and should have the radiation boundary for the air box around the design. And you can see everything that we've designed so far right here. Alright, so the only thing left for us to do is to do the solution setup. So under analysis, if you right click, add solution setup, advanced. Just gonna go make sure that okay, no problems. Okay, so solution setup, advanced. So now for the microstrip line, it's usually used for relatively low frequencies, so maybe up to 10 gigahertz. For now, let's say I'm only interested in frequencies up to, let's say, 6. So I will set 6 as my solution frequency. Maximum number of passes, let's say 10. Maximum delta S, I'll leave it the same as the rectangular waveguide. So I'll just say 0.01, which is really good. I'll just leave it as that. For options, minimum number of passes, I would really want a good conversion, so I'm going to set 6 minimum number, and minimum converged, I'm going to say 3. So exactly the same as last time. And then okay. And let's say I'll leave it as interpolating sweep, and let's say I'm interested in frequencies between 1 and let's say 3. So I'm only interested between 1 and 3 gigahertz. And you notice that the frequencies of interest are less than the solution frequency. So the solution frequency was 6. I'm only interested between 1 and 3. So that's a good way to do it. And then okay. So you have your solution, you have your frequency sweep. So the only thing left to do is to validate. So you want to validate, everything's good. And once you validate, you can click on the design and analyze all. So just to note, if you click on the project and say analyze all, it's going to analyze every single design in the project. But sometimes you just want to analyze one design. So if you just click on the design and say analyze all, then it's just going to analyze that one. Yeah, so simulation should be running. How did you mirror the port? Okay, so what I did is I copy and pasted the wave port, and then I just changed the Y dimension. So I'm going to show you that now. So I copied wave port 1 and I pasted it, and then I just changed the Y dimension from 0 to sub W. Although you can mirror it if you want. You can mirror it along the middle of the substrate, but this is a really simple change, so I just did it manually. Analysis parameters. Okay, I will go over them again. So for so if you go under analysis, if you right click solution setup advanced, then you will get to the analysis, which I will show you now. So you'll get here. So the solution frequency I set was 6. Number of passes, maximum number of passes was 10, and then my maximum delta S, or you can think of this as your convergence criteria. The lower this number, the more strict your convergence criteria is, but 0.01 is fairly good. And then under options, minimum number of passes is 6, minimum converged passes is 3. So that's for the solution parameters. For the sweep, I have an interpolating sweep from 1 to 3 gigahertz and 4 to 1 points. No problem. Okay, so for those that just finished their sweep, I'm just going to give you a few minutes to make sure that your design has run and finished. For me, it's done. So as you guys should have known by now, we always check for the conversions when the design is done. So if you go into results, solution data, conversions, that's the first thing you want to check. And I'm going to ask you guys this. The solution's done. I'm looking at my conversions, and it says it's converged, but the target was 3, and it converged only twice in a row. So what it means is that it finished the maximum number of passes, and it only converged twice. Now, is this good or bad? It really depends. Like in my opinion, since it's already converged twice, and I can see that the numbers are going down, if I look at the plot, like it's already past the point, I can say, okay, this is good enough for me, I'm going to stop. But sometimes you can say, okay, I actually want it to converge 3 times in a row. So what you would do is you would increase the maximum number of passes beyond 10 so that you can actually get the 3 consecutive converges that you want. So again, this is up to you. For a microstrip line, the performance or the characteristics are fairly known. So if you get something strange, then you would know that you need to run for tighter conversions. But if it's a completely new design and you're really interested in knowing the characteristics of it, then you might be more strict in the way you accept conversions from HFSS. So I would say this is good. It converged twice. I wanted 3, but that's good enough. And again, you can see here the number of passes. It finished all 10, but it could have gone more if you had more passes. Okay, so I think everyone's solution must be good by now. So let's look at the results. We'll do the same thing as last time. We'll look at the S parameters. So if you right click on results, create modal solution data report, rectangular plot. We'll do the same thing as before. We're going to look at S11 and S21. So create new report. All right, so these results are expected, but you have to be careful. So remember the way we define the waveport. We chose to not renormalize, which means the waveport took on the impedance of the line, and what that means is that your design will always be matched, because your waveport impedance will take on whatever impedance of the line that you have. So if the line was 20 ohms, the waveport will be 20 ohms, and you are fully matched. Which is what we see here, which is good. But you also want to make sure that you check the actual impedance, because in a physical structure, your connector will not take on the impedance of the port. It will be an actual impedance. So it'll be like 50 ohms. So that means the line has to be 50 ohms in order to get this nice matching. So nice matching is low reflection and very high transmission. So now let's actually check the port impedance. So if you go under results, again, modal solution, rectangular plot. This port Z0 tells you the port impedance of the waveport. So if you create new report, so you can see here that the impedance of the port, like I told you guys before, I chose the width to be close to 50 ohms, and it is. So it's between 50 and 50.3, so it's almost 50 ohms across all the frequencies of interest. So that means if the port impedance is 50 ohms, and your line, so that means that the line impedance is 50 ohms, and if you take this transmission line and connect it to a connector that's 50 ohms, then you would get the expected results. Okay, so that's the port impedance I want to show you guys. Now let's run a parametric sweep where we change the width of the line so that we can see this impedance changing. And we'll also show you guys how to run a parametric sweep in HFSS. All right, so let's just double click on the design so we can see the design again. Now, for a parametric sweep, it's really easy now because we have variables. We can easily change things. So if you go under Optometrics, add parametric. So again, Optometrics, right click, add parametric. You get to this window, you want to add a sweep. All right, so what variable do we want to sweep? We want to sweep the width of the line. So that would be microstrip width. And let's say we want to have a linear step between 1 and let's say 4 millimeters, and the step is 0.5. So once you've done that, click on add and make sure it's there. If you don't click on add, if you click OK, it's not going to go there. So you have to set the start, the stop, and the step, and then click on add, and then OK. So now you have a sweep for the microstrip width. It's a linear step from 1 to 4 millimeters in steps of 0.5. If you go under table, you'll be able to see all the dimensions that it's going to run. So there's going to be seven simulations for each of these dimensions. Okay, so while we're on the topic of 7 simulations, so that means you want to run this design 7 times. There is a way in HFSS that you can run these all these sweeps at the same time, and that's what I'm going to show you guys next. So once you have this, you have the sweep all set up, you can just click on OK, and the parametric sweep is there, and it's enabled, so that's good. All right, so if you run if you analyze all right now, HFSS is going to do 7 simulations right after each other. But ideally, we want to run them all at the same time because the server has the capabilities of doing that. So follow me and I'll show you how to do this setup. So tools, options, HPC and analysis options. All right, so the first thing you want to do is let's go under here and click on edit and uncheck use automatic settings. And now tasks and cores. So the server has more than one core, and what you can do is you can run each simulation on a different core at the same time. So we have 7 simulations to run. So let's say we can do like 10 tasks for 10 cores. So that means up to 10 tasks or up to 10 simulations you can run simultaneously at the same time. I'm not exactly sure what's the maximum number of tasks that you can select. It probably depends on the number of cores, but I usually do 10 because it's good enough for the speeds, and usually we don't need to run more than 10 simulations at the same time, or 10 sweeps, or 10 values in each sweep. You can leave GPUs as 1. I don't think that affects it. Okay, so once you have that, you can say 10, 10, 12, 12. I think if you choose more tasks than cores, it's going to give you an error. Just make sure the number of tasks and cores is the same. Okay, so once you click on that, that's good. The other thing is you can enable the GPU. And from that, you go under options. And you can see here, enable GPU is false. You can select that as true. So that's going to speed up your simulations significantly. Okay, so once you have that enabled, you can say OK. And now we can run the simulations, and you'll be able to see what I mean about running them simultaneously. If you go under simulation, you want to validate, make sure that everything is still good with the design. And if you analyze, again, just make sure you select the one design that you're interested in and analyze all. All right, you can see here it's going to start the sweep, and it's going to solve all 7 simulations at the same time. If you had 20 simulations, then it would solve 10, and then there'll be another 10 waiting in line, because remember we said the tasks and the number of cores to be 10. So right now this will be a fairly fast sweep, because it's running them at the same time. Hopefully everyone got that, and if you didn't, I can always explain it again later, and I think I have a document explaining the steps to that, but for now it should be running at the same time. And you can see here as the solutions are done, it's going to say it's solved 1. There's 6 remaining to be solved. And just so you know, each one of those is going to have its own conversions. So if you're on the edge of conversions, which we're not now, because the conversions is really good, you want to go and check the conversions for each one of them. And you can do that in the results, but I'm not going to go over that now because we're running late. Okay, so the sweep is done for me. I'm not sure about the rest of you guys, so I'll just wait a minute or two for everyone's sweeps to be done. This error here that I got, I'm not sure if the rest of you guys got it, but it does seem like there wasn't enough licenses to run them in parallel, but it did solve the sweep anyway. So we'll see. We'll see what happened. Okay, so now we have 6 or 7 simulations with 7 different results. Now let's check the port impedance. So as you guys know, if I change the width of the line, the impedance should change. So if the line is wider, the impedance should go down, and vice versa. So if you double click on your port impedance, you can also create another one. So let's do that. Create modal solution, port impedance. Now if you go under families, so trace families, you can see that the variable has showed up here, and what you can do is you have 8 different solutions, and you can show all of them, and that's what's selected by default. So you can select each one independently if you want to show it, but you can also show all the variables at the same time, and that's what we're going to do. So show all solutions for port impedance for all dimensions of the microstrip line. So if you click on new report, there you go. So depending on the width of the line, the port impedance is going to change, because we set it to take on the impedance of the transmission line. So if the line is 1 millimeter, the port impedance is 80 ohms, and then as the width increases, the impedance goes down, as you would expect. So again, this exercise was to show you guys how to create a parametric sweep and how to view the results for different results, such as the port impedance. Okay, so that is the end of the microstrip line. So I'm gonna save that. Okay, so I was hoping that we can get to the coax cable, but I do want to give you guys an ADS overview as well. So I think we'll stop right here for HFSS, and we'll move on to ADS. So make sure that your project is saved. So save project, and it should be where you selected the directory. So I know a lot of you guys don't have an H drive. I'm going to ask Nagy about that, so make sure you send me an email with your CMail username and I'll make sure Nagy sets you up with an H drive. So one thing I wanted to make sure you guys know, so I'm just going to close that and go to the project. So I'm just going to close that here. Once you're done from HFSS, make sure that you close the window, because we have a limited number of licenses and there's a lot of courses that are using the software. So when you're done, if you're not running a simulation, make sure that you close the window, because if we notice that there's a lot of windows open and no simulations running, we might have to shut it down. And if your design is not saved, that's going to be a problem for you. So if you're done using HFSS, just close the window completely. So that's the first thing. The second thing is the results. So that's the folder that I saved the design at. Your actual project file, which has all the information that you need to produce the results, is this one right here. So that one is just called ANSYS electronics desktop file. All you need to reproduce the results is this file, the results file, and this file, as you can see, it's not very big. The results folder, on the other hand, it saves all the results in your project, and that one can get really big. And because everyone's using the licenses or everyone's using HFSS and saving the results, the H drive can run out of storage very quickly. So once you're done taking the results, you can just delete this file. And when you're sending me your file, let's say you're running through a problem, I don't want to see the results file because I can reproduce the results using this HFSS file right here. So this one, whenever you can, whenever you're done, just delete that because it takes up a lot of storage of the H drive. So I'm just going to go ahead and delete this results file. And I'm not going to lose anything because I can always reproduce these results from the project file right here. Okay, so we're done with HFSS for now. I'm just going to take like a few minutes break and then I'll come back to you guys and we'll discuss ADS next. So yeah, we couldn't get to the coax cable, so we'll discuss ADS and then the coax cable I can show it to you guys another time. Okay, I'll be right back. All right, guys, we have about 45 minutes. I think we can make some progress on ADS. Okay, so ADS is different from HFSS in a few different ways. So ADS is mostly for circuit analysis. If any of you guys are doing 4502, you'll be using mainly ADS for your designs. It's a lot faster than HFSS, but it's also less accurate because I think it's not rigorously solving Maxwell's equations. I think it's using other approximations, but it is a lot faster. And throughout the course, whenever we can, we will compare results from HFSS to ADS, and they do match fairly well. Yeah. Oh, it doesn't? Oh, okay, so Eli doesn't have. I'm a bit surprised. Did you check, Adam? Okay, so Christina's license works on 204. So 204 is Eli. Okay, can we get a few more? Adam, can you check? It's I think it's called update 2. It's Okay, let's hear from a few more people. Yeah, it's expiring in 16 days. That's right. Okay. Okay, so if you cannot open it, well, let me check. Well, I guess you can just go onto the server that I'm running on. So if you go on if you just type the name of this, if you're already in, right? So don't log out of the server. Just go on remote desktop inside here, and just type the name here, Amy2, and it's gonna be the same thing, username and password, same as the server that I gave you. So try that, and hopefully it works. It's strange that it's not working for some people. Okay, so the guys that can get ADS to work on Eli can go on Amy2, and it should work there because I checked. Okay, while you guys get that going, and go back to the presentation. So it's I find it fairly intuitive to use ADS because it's a simple circuit designer, and so today I'm gonna try to show, let's say, the attenuator and the microstrip line, because the bandpass filter has a similar design method to the attenuator. So I'm gonna show you guys the attenuator and the microstrip line on ADS. Okay, so hopefully you guys got on the server. Adam? Okay, alright, so we'll perfect, yeah, so 16 days left. Yeah, I told Nagy, and he'll take care of that. So let's get on ADS. Alright, so ADS is under advanced design systems. So if you search for advanced design systems, it's update 2. So it's that one, advanced design systems 2020 update 2. Probably get the license. Yeah, don't worry about that. So it'll be taken care of. So you just close it. So you can say you're new to ADS. Okay, so like this will be the place where you select the components. The wires are there. The simulation controllers are here. The simulate button is there, and I will go through all of that. It's a good guide. Got it. Okay, so if you guys open it for the first time, it should automatically have created a schematic for you. So, but in case you don't have a schematic, I'm just going to exit that. Okay, and I will create a schematic from scratch so that everyone can see it. So this is the project window. There might be a schematic already there, but we'll create one from scratch. So if you go under File, New, Schematic, that will create a new schematic in ADS. You can give it a meaningful name. Let's say the first one is the attenuator. Create a schematic. Thank you. Okay, I'm just going to exit these steps. All right, so this is the design window in ADS. The first design is a simple 3 dB attenuator in a pi network. So that's 3 resistors, 1 series, and 2 shunt. So the components that you will use will be in this window here. So the basic ones are shown by default, but you can also select other components. For now, we'll just use the lumped components, so you can just leave it at that. You can also search the library for other components that you need. All right, so the first component we just need resistors. So if you click on resistor, you can just place it somewhere. We need 3 resistors, so we just need 3. If you need to rotate it, it's Control R, I think. Yeah. So Control R on your keyboard will rotate the component once you have selected it. So I need 3 resistors, so like that. Okay, so 3 resistors. Next we need to connect them with wires. You can move them around. So now the wires are here. Insert wire. Simply just connect them. And then we also need a ground. So I'm looking here. Is there a ground? Yeah, I don't see the ground that I want, but I can always search for it. So if you go under libraries, you can search. So the thing is, you have to know the shortcuts for the components. So I don't know if I type ground. Yeah, okay. If I type ground, it's gonna get it. So if I go here, there you go. So you can search for ground. I couldn't remember if it was GND or ground, but it's ground. And once you have ground, you can just add the 2 grounds. All right, and that's the basic circuit. So this is the equivalent of putting in the model in ADS. Next thing is you have to define or create a solution or a simulation that you want to run. So for this one, we want to run an S parameter solution. So you guys may or may not be familiar with S parameters, but usually they characterize a network, a 2, 3, 4 port network. This one here is just a 2-port network. We send in power or voltage here, and we monitor the output. Actually, before I do that, let's actually put some resistor values, because by default they're 50 ohms, but the attenuator has different values. So a pi attenuator that I have, it could be any numbers, but I wanted it to be a 50 ohm pi attenuator, a 3 dB 50 ohms, so that will set the values of the resistors. So the series one is 18 ohms, so you can just type 18. The shunt are 300 ohms, both of them. All right, so now we have the resistors, we have the values. Now we need to add an S parameter simulation block. And what the simulation block does, you guys will see. So if you search for S dash param, S parameter simulation, if you click on that, then you can add this block for an S parameter simulation. Make sure everyone is okay. All right, so for this pi attenuator, let's say I want S parameters from 1 gigahertz to, let's say, 3. And the steps, so of course, if it's just 1 gigahertz, it's only 3 points. That's not enough. So let's say a step of 1 to like 1 meg. So it should be enough points. And for every S parameter simulation, you need to define a port. Right, so let's move that up there. You need to define an input port and an output port to measure the network with respect to. So you can think of the port in real life as your connector. So this circuit, if it's on a board, if it's on a PCB, you're gonna have connectors on either side. So the port that you're gonna define here is that connector. So if you just add a port, no, it's not that. Oh, it's a terminal. My bad. So it's a port impedance termination. So it's a term, not a port. So you search here. But again, it's a termination, port impedance termination for S parameters. So a lot of times, your connector is a 50 ohm connector, so that would be your termination, and you need that on both the output and the input. So you can create another one here and put it on the output. And same idea for the port. You're gonna need the ground. You can copy and paste. Just, copy paste the ground. Escape, and then you can connect with wires over here. Okay, so this should be good to go. So you have your 2-port network, you have your input terminal, you got the output terminal, and you have an S parameter block to run the simulation for that. And once you've done that, you can click on the simulate button right here, and you guys will notice that ADS is very fast, a lot faster than HFSS. It's almost instantaneously runs your design, and it brings you here to this window, and that's where we can see the results. Before I go there, though, I want to make sure everyone is on the same page. So if there's any issue, let me know. Okay, so you got an error. What does the error say? Could not open file. Okay, I'm gonna go back to the simulation, and I want to make sure that you have the same components that I have. So you need, I'm gonna go back to it here. All right, so you have 3 resistors, a ground. You have the 2 terminations, all connected together, and these 2 have grounds. And you have an S parameter block with a start and end and a certain step size. So make sure that you have all of that. Same error. Okay, I don't know what the error is, so I don't think I can help you right now. But again, I will upload the file. Standard commands line. Okay, is everyone getting the error? Or just okay, it's possible. Are you guys using the C drive? Like your local? Okay. Virtual C drive. Okay, I don't know what the error is, but what you can try, it might be a problem of running it on this virtual C drive, possibly. You can try running on the server itself and see if that helps. If not, maybe we can do a one-on-one, and you can share your screen and you can see what's wrong. But for now, you can just follow along. Again, the session is recorded, so you'll be able to view it later if it's still not working. But yeah, sorry, I don't know what the error is. Okay, we'll go back to it and and if there's still a problem, we can debug later on. Okay, so for those that it worked for, if there's no error, you wouldn't get anything that says an error. But you'll get to this window, and in this window you can plot the results. So you can plot, again, similar to HFSS, you can have a rectangular plot, you can have... Okay. Oh. Okay, let's give it a moment. You can still hear me though. Okay. Okay, I'll wait a minute to see if it improves. Okay, I'm moving the window around. Still choppy. Okay. All right, thanks for letting me know. Yeah, just keep me updated, because I wouldn't know if it's working or not. So if there's anything, keep me updated. I appreciate it. Oh, you can't see the server at all. Okay. Okay, let's wait a moment. Okay, maybe I'll try to stop sharing and share again. How's it now, guys? Okay, let's see. Okay, so some people are saying that it's been on and off all session. Okay. So is the sharing is working? Okay, so can you see the ADS window now? Okay, so yeah, if it ever happens, just let me know, so we can fix it. Okay, so hopefully this is good for everybody. Just, can't see screen. Yeah, okay, I think we went here. Okay. All right, so similar to ADS, to HFSS, you can plot using either a rectangular plot or a Smith chart or other things. We'll look at the rectangular plot for now. So if you just click on rectangular plot, you can place. Okay, so you can select the variables to plot. You can add them and then press OK. It's a good help. So let's look at the similarly S11 and S21. And select and shift. Select. Shift command. Alright, let's add them independently. So add S11 in DB and S21 in DB as well. So you click, add, and then you can see it here, and when you press OK, you can see the two S parameters on this plot. So as you guys can see, the reflection is low, and it's because I designed the attenuator to be 50 ohms. The transmission or the attenuation is actually 3 dB, exactly like I wanted, so you can insert a marker here, and you can see that it's almost 3 dB attenuation as per the design. So so far so good. Okay, perfect. Yeah, I was just waiting just to make sure that I'm not talking to nothing. All right. So it's doing exactly as expected. So we can just minimize that for now. Um, what I wanted to show you guys here is how to create variables and play with the tuning. So right now, all of these values are just entered by hand, but we can also create variables so that we can change them later on. So for that, you need to find the variable block. So variables and equations. So just click on search var and just click on that. You can create this variable block. And if you double click, you can go inside, and here you can add a lot of variables. So you don't need to create a block for every variable. You can just add all of them here. So let's say the first variable, I will create it for the series resistor. So I'm just going to call it series R. And I'm going to say, so that's 18 ohms right now. So you can apply. So now we create a variable series R. You can also add another one. All right, and we can just go here and we can say shunt R. And that one is 300 ohms. Here. And add. So now you have two variables, series R and shunt R. You click OK. And then you can go over here, and instead of the number, you can just enter the variable that we selected or that we chose. So you can just say series R and shunt R here. And since the variable is just a number, it's going to take on the unit of the component. So shunt R. Okay, so you can run the simulation again, and nothing should have changed because it's just the same numbers. But now that they are variables, you can do some tuning and look at the results in real time. And that's one of the reasons why ADS is really powerful compared to HFSS, because HFSS takes a lot of time to run the simulation, so you can't really tune and look at the results at the same time. But in ADS, you can do that. So if you find this fork here, if you click on that, that's the tune parameters. Okay, so right now there are no parameters to tune because we did not make them tunable. So you actually have to go to the component and allow that the parameter to be tuned. So let's exit that for now, and we have to go to the component, or actually maybe the variable itself to make it tunable. Let's try that. If you go under the variable, if you go tune, then you can enable it right here. So you can enable the tuning. You can select the maximum and minimum and the step size. So let's say for the series resistor, we're going to go from, let's say, 10 to 30 and step size of 2. And then we can do the same thing for the shunt resistor. Enable it, and yeah, that sounds good. 150 to 450 in steps of 30. Okay, so series and shunt both are enabled for tuning, so you can click OK, and you can see this T that shows up beside them. That means you can tune them. Okay, let's give this another shot. Click on the tuning. So let's put this window here, and let's see if we can find the results window and put it beside it so you can see both of them at the same time. Okay, so let's play with the components and see how this affects the attenuation as well as the matching. So remember, the port impedance here is 50 ohms, and the matching is determined based on the port impedance. So if the network, which is the attenuator, is not 50 ohms, then you would start to see a lot more reflections. But right now the reflection is below -40, so it's almost negligible. So okay, so let's play with the tuning. So if I start to play with that number, you can see here that the attenuation is changing. You can play with the shunt. And if you want to go further, you can simply just change the minimum over here. You don't have to go back to the variable, and I can go further down. Okay, so tuning is one of the really good things about ADS, and again, You can't really do that in HFSS because of the simulation time. You actually need to run the simulation, or remember we ran the sweep, and then we have to look at the results after the fact. But over here you can simply tune and look at the results at the same time. And then if you click on close, it's going to ask you, do you want to save the tuned values back to the schematic? I'm going to say no. But let's say if you were optimizing something and you found some good numbers that work in the design, then you can just say save it. For now, I will say no. Okay, so once you're done, you can just you can save the results. And I'm trying to remember. I think this one might have saved. Okay, let's say save as. I didn't save that in the H drive. So let's save as. I'm trying to see where. So it's saving it in the C drive, which is not what I wanted. But let's. You can save it somewhere else. It seems like it's running on the C drive. Save a copy, maybe. Okay. Save. Okay, I'm not sure where this went. It doesn't seem like, can I change this? I can't change it. Okay. To be figured out. Alright, so we'll save that for now, and then we'll go on to the microstrip line, which is something that we can directly compare with HFSS. I don't think we'll get to that today, but I'll show you guys how to create a microstrip line on ADS. So you can close that schematic, and then we'll create another schematic. So File, Open, Schematic, and we'll call that microstrip line. Got it. Okay, so microstrip line is a similar idea. So instead of a component, we have a block here, which is called I think it's microstrip. I'm trying to remember. I think maybe trace microstrip line. So you have a lot of options for microstrip. So the line is MC. So these are coupled lines. Okay, if we go MC, MS. Okay, let's check the substrate first. So the M sub block will define the substrate. So let's click on that, and let's say we want a standard millimeter layout resolution. Okay, so if you missed the last step, I just went MS and I found the M sub, which is the substrate block in ADS. Click on finish, then you can place a substrate block here. So the substrate block, it defines the properties of the substrate that the line is going to go on. So let's say we want the same properties that we had for our HFSS simulation. So the height, if you guys remember, was 1.27 millimeters. That'd be the height of the substrate. Epsilon R for FR4 was 4.4. Conductivity, you can leave that as is. HU you can leave as is. The loss tangent, which is tan delta, that was 0.02. If you remember from FR4. Alright, so that defines your substrate. So now let's see if we can find the microstrip line. So if you can't find it, you can always go under here and see if you can find the block where it belongs. So transmission line microstrip, that's probably where it belongs. So if you go here, then you can see all the microstrip lines, and there it is. So it's called MLIN, and that's the microstrip line that we need. So there you go. And right away you can see that it has chosen the block for from M sub. So M sub will be the properties where the substrate is going to extract the properties from here. And then you can define a width and a length for the line. So let's say the width of the line for 50 ohms, if you guys remember, it was no, it wasn't 1.27, it was 2.43. And the length of the line, let's put it as 50 millimeters. All right, so we have the line, we have the block. Now we need to put in the terminations. So just like before, we need the termination, which is like your connector. So port impedance termination, we can put that here for the input, and we can do it again for the output. So same idea. It's a 2-port network, and these are the terminations for the network. And we need the ground. So I think there are shortcuts for ground, resistor, and maybe other things that you can just simply click a letter and then it brings up the component. But I'm not familiar with that. But you guys can look at the help file and you might be able to find it. So I know I'm going to find ground here, but there might be a shortcut like G or something. Put a ground. And then just connect it with lines. Okay, so now we have defined the network that we want to test, and just like before, we want to look at the S parameters. So this is going crazy. Okay, we want to look at the S parameters. So we need an S param block. So let's look for S param simulation. So let's say we are interested for let's do 1 to 3 again, and steps of 0.01. If you guys go under the properties, you can select like instead of gigahertz, you can select steps of like I don't know, 2 megahertz. So there's a lot of options here that you can play with, and that's the number of points. You can see here that for ADS, a lot of points is okay. The simulation is still fast as opposed to HFSS, where you have to be careful about the number of points. But also this is less accurate. So, oh, didn't do the steps. Apply. 1 to 3. Interesting. Okay, let's see what it does. All right, I don't see the steps here. Okay. All right, so once you're done that, you can just simulate. And same idea as before. Okay, simulations did not include metal loss. That's fine. Okay, let's look at S parameters, and you know what? This time let's look at the Smith chart. I think you guys are familiar with the Smith chart. It's another way for presenting the S parameters. So say got it. So let's plot S11 on the Smith chart. So let's plot the reflection. And the Smith chart assumes it's normalized to 50 ohms. So if you guys remember, if the S11 is 0, it's going to be in the center of the Smith chart. In other words, it's matched. And there we go. So from 1 to 3, the S11 is at the center. So that means your line is matched to 50 ohms. Let's see if we can do the same thing as before with the tuning, so that we can see changing the width of the line will actually change the impedance from the center to somewhere else. So let's do that. So we'll do a variable just like before. So let's create a variable. We'll just double click on that. We'll create a variable called microstrip width. And we can define that to start as let's say 2.43. Why not? And then for tuning, we want to enable it, and let's say we want to go from 1 to 5 in steps of 0.5. modify that. Okay, so now we can change the variable name here to MSW, and let's tune it. And let's look at the S parameter or the Smith chart here so we can see the effect. Here we go, Smith chart, tuning. All right, so when the width of the line is exactly 50 ohms, you expect it to be in the center of the Smith chart because it's normalized 50 ohms. So now if we play with the tuning, we expect this point to move away from the center, and you will see that we also start to have, so this circle here is because we're running for a frequency sweep. So at every different frequency, the line has a different impedance, or the reflection is different at different frequencies. And if you guys can see here, like I'm increasing the width of the line, and on the Smith chart that corresponds to a lower impedance, because this way is lower impedance, this way is higher impedance. It's 0 here and infinity here. If I go the other way, then I would go the other way in the Smith chart. And again, you can reduce the step size, you can reduce the minimum value if you want to go a bit lower. If you go all the way to the highest, you can increase the maximum value if you really want to increase the width. And compared to what we did in HFSS, we had to run the parametric sweep for 7 points. It took some time, and then we viewed the results. But over here, you can simply just tune and see the results right away. So that's the advantage over HFSS. Okay, so this is all I wanted to show you guys for the microstrip line. So I'm going to save that. And just like HFSS, when you're done with your design, make sure that you close it. And I don't think the results here take up as much space, so you don't have to worry about deleting the results file. But just make sure that you close it and save the design. Okay, I still gotta figure. Yeah. Yeah, absolutely. Yeah. So by the way, the design is on the C drive. So I can move that later on. But okay, so the tuning. So I'll go to the microstrip line. So if you click on the schematic, there's gotta be a way to get rid of this. Okay. So to tune it, you need to have a variable, and the variable needs to be tunable. Right? So over here, I created a variable block with the variable ms_w, and inside I made it tunable by enabling tuning right here. So it's enabled, and I set a minimum and a maximum, and a step value. So once you have that, you have a variable, it's got a t beside it, and this variable is inside here, inside your microstrip line. And then when you can run the simulation, and give you some results, and then you click on this fork right here to tune. So if you click on that, and that's all right. No problem. All right, so I think that's good for today. I wanted to show you the coax cable, but next lab will be on coax cable, so I can show you that in the demo itself. So I'm gonna go back here. Okay, so this is the end of the workshop. We still have some time if you guys have any questions or any concerns. So again, the session is recorded. I'm gonna upload it. I think Blue Button saves it somehow. I'll figure this out at the end. And it will be available to you guys after the lab. The files I'm going to upload as well, but this is just for that lab so you guys can see what I've done. And do we send you an email if we don't have an H drive? Yes, please do send me an email and we'll figure it out. So for that error, I don't know what the error is, but okay, maybe you guys can send me an email and we can figure this out, so we can have a meeting separately, and I can see what you guys are doing and see if we can figure it out. Perfect. Okay, so just some final comments. Again, remember to, can you email if you find fix? Okay, that's not for me. So when you guys are done using the licenses, please make sure you close them, because we have a limited number of licenses and there's 2 or 3 other courses that are using them. So when you're done, just close the software and do that for HFSS and ADS. For HFSS, the results folder takes up a lot of space, so if you can just periodically delete that as you go. Again, you don't lose your project, you just lose the results, which you can always reproduce later on. That's all I have for today. I'm here if you guys have any questions. If not, thank you for attending, and I'll see you in 2 weeks. So there's no lab report for this one, but for lab 2 to 5, there's going to be a report. Awesome. Thank you guys. Take care. Yep. Okay. So did you see the document that I uploaded on CLR? Okay, and your username didn't work, or what was the issue? Okay, send me an email. I don't know if you may have registered late into the course. Okay, it might take some time for it to be done automatically, but send me an email and I'll get it to Nagy, and he's gonna take care of it. No problem. You too. Take care.